the main purpose of our lab is going to be applying energy conservation principles of circuits to study their behavior and how different arrangements of resistors and capacitors interact, modeling these circuits in an online circuit modeler, and using multimeters within the circuit to measure conventional current and the potential difference. Our experimental time constant was 5.917 seconds, and the theoretical value calculated was 6 seconds. So the main fundamental principles are going to be conservation of energy within a circuit. The circuits that we are studying are steady state, and as well as Kirchhoff's current law, such as the loop rule and the node rule, where current will split or combine at a node. We also have Ohm's law, where voltage equals current times resistance. We have capacitors and resistors in series and parallel, and the time dependence of RC circuits, where the time to charge a capacitor fully is going to be equal to the resistance times the capacitance. So the main assumptions we're going to be making in this experiment is that the circuit that we're building is ideal, so we can ignore the resistance of the wires and ammeter. They're essentially negligible, and the system is going to be our circuit, and since we are doing this in an online program, we can assume that our circuit is ideal. So our first circuit we made has two 1.5 volt batteries, 2 ammeters, and 2 resistors, and our measured current was 0.02 amps, and that value matches up with our calculated current at the left side, where we found the equivalent resistance of 147 ohms, and using the voltage of 3 volts, we also got the same value of 0.02 amps. So when we replace one of the ammeters with a voltmeter, we get that the current is 0 because we've essentially broken the circuit, so the potential difference remains equal around the circuit. But the voltage we measured is going to be 3 volts, which is equal to the 2 batteries added together. Then we measured the voltage between different points, and we want to see that the sum of all these potential differences adds up to 0 volts, which is consistent with the loop rule. So we can see on the left side all the different points that we measured the difference between, and when we sum them up, they add up to 0 volts. The current also stays the same in the situation like the previous circuit and stays at 0.02. Here we have the graph showing the potential difference of the different points we calculated from the previous slide. So we can see the graph goes up to 3 volts, which is the voltage that the batteries are supplying, and goes down based on the potential difference between those different points. And we want to see the graph go back to 0. Next, we placed an ammeter in parallel to the 100 ohm resistor, and we can see that the current reading increases to 0.06 amps. And this is because the current now splits at the node between the 100 ohm resistor and the ammeter. And because the current is now splitting, we also see that the resistance decreases due to the presence of the ammeter, the overall resistance. So this allows the current to increase. We can also see the calculated resistance values at the bottom based on the potential difference values from the previous slide, and we can see that our calculated values of 48 ohms and 102 ohms are very similar to our actual resistance values of 47 ohms and 100 ohms. Next, we introduce a light bulb into our circuit. So now we have a 9 volt battery, a 200 millifarad capacitor, and a 10 ohm bulb. When we attach the circuit, we can see the light starts really bright and then dims really quickly, and the current goes down to 0. Next, when we disconnect the battery, it does the same thing. The light gets really bright and dims again, and the current also reduces from its maximum all the way down to 0. We actually measured the time for the capacitor to charge and discharge with different resistance within the light bulb that it's connected to, and we can see as the resistance of the bulb increases, the time to charge and discharge decreases. And this is because as we increase the resistance of the bulb, it's going to be harder for current to flow throughout the circuit. Next, we set up an experiment where we had the battery, the light bulb, and the capacitor, and we measured the voltage across the capacitor at different time points over a span of around 20 seconds. We then took these values and took the natural log of the voltage measured over 9 volts, which is the original voltage, and modeled it and found the line of best fit. We're going to use this line of best fit to find the time constant of the circuit. So we can find the time constant by using the formula RC equals -1/slope, and that gives us a time constant of 5.917 seconds. And the theoretical value can be found by multiplying the resistance by the capacitance, which is going to give us 6 seconds. If we were doing this lab in real life, the real ammeters will have some resistance. So this is going to contribute to the current readings being lower than in the experiment, and this is because as we increase resistance, our current is going to be slower. If we remove the resistor from the circuit and use a battery charged capacitor, in an ideal model, we would see this capacitor instantly reach full charge because we can see if there's no resistance, then the time constant is essentially going to be 0. But this won't happen in real life because the wires of the circuit still provide some resistance, even if we considered it negligible for the sake of our model in this experiment. So our time constant is going to be lower than the one we just calculated, but it's going to still have some time until the capacitor can reach full charge. So the main sources of error for this experiment is going to be not getting the most accurate values of when we stop the stopwatch and measuring the voltage. So improving that can allow us to get a closer value to the ideal time constant that we calculated, and this is mainly due to human error. So from this experiment, we're able to learn about the time constant to see how long it takes to charge a capacitor in a circuit, and how these values are going to differ in an ideal and real circuit is something we can continue to study.